Hello everyone. So we have already passed 3 weeks on this course theory and applications in thermal and cold plasma. So in this class, what we will try to do, we will review the key concepts that has been covered in the last 3 weeks. So this 3 weeks have covered the concepts like this thermal and cold plasmas, plasma the fourth state of matter, ionization, recombination, diffusion, mobility, Saha ionization equation, plasma species distribution, then plasma collective behavior, charge neutrality, space and time scales, plasma seed, concept of temperature, Debye length, plasma oscillation frequency, plasma parameter, criteria for plasma state. Then we have also covered the collisions in plasma, small and large angle scattering, then this collisionless approximation, the equilibrium and non-equilibrium models, then elementary fluid theory of plasmas and MHD equations. So basically these are the basic concepts covered, and what are the key features in these terms that we have just uttered now, that we will try to understand and that we will try to emphasize what are the key points that we have learned in the last 3 weeks. So to start with, actually we grossly defined a plasma like this. It is a large collection of positively and negatively charged particles which is sufficient to shield itself within a distance of characteristic length, that is called plasma. Okay. Now plasma is macroscopically neutral but microscopically non-neutral. So when we are thinking of a system which is called a plasma, definitely we are thinking of large collection of positively and negatively charged particles, and those negatively charged particles are usually the electrons, and positively charged particles usually ions, that may be single ion or double ion or triple ion depending on the temperature of the plasma. And the system should have volume large enough so that it can shield itself within the volume. So that is what we are calling a characteristic length. Now some of the striking features, as you know, we started with telling that plasma is the fourth state of matter. Now why this is fourth state, why it doesn't belong to your solid, liquid and gas, why we need to tell them a different state altogether they belong to. Now several of the things which make them distinguishable from the other three forms of matter, that is solid, liquid and gas, are like this: that plasma is composed of electrons, ions and neutrals. Plasma is macroscopically neutral. Plasma is microscopically non-neutral. Plasma can well explicitly respond to electric and magnetic field. Why? This is because they are containing the charged particles. So charged particles respond to electric field, and you know that whenever they find a magnetic field, they start rotating around it. So they respond well to electric and magnetic field. And when a specific external electric field is applied, charged particles of both polarity in plasma can drift in the same direction. That is very peculiar, because ordinarily if you apply an electric field, then this positively charged particles will move in one direction and the negatively charged particle will be moving in some just opposite direction. But there is something called E cross B drift, in which you will see that you have already gone through in the classes that both positively and negatively charged particles are drifted in the same direction. Now when charge neutrality is disturbed, the electrons start oscillating at a frequency precisely decided by the number density of the electrons, because the restoring force comes from the number density. Now plasma can shield itself within a characteristic distance. Okay, that is precisely determined by temperature and prevailing density of the charged particles. So, these are something which are very, very particular to the kind of plasma that you have created, what is the number density and what is the temperature. For example, if you are ordinary gas, you just think of that, then it neither reacts to electric field nor it reacts to magnetic field, okay, and neither it shows any oscillation frequency, okay. Now, so all these parameters are very particular to the plasma state. So, plasma also behaves as a refracting media, and refractive index is decided by again the number density of the charged particles. So, what we are seeing that plasma is mostly in the gaseous state, but it is different from the gaseous state. So, it responds to electric field, magnetic field, and it behaves as a refracting media, and the number density and the temperature decides what will be the shielding length, because within there is a characteristic length within which it can be non-neutral, but beyond which it can be showing it as a neutral system. So, all these properties are very particular to the plasma system that we have learned, and that is why they are different from the other three states. Now, then we went through the potential of the plasma that can be applied in various industrial applications. So, starting from novel material synthesis, electronic industries, agriculture, medicine, waste management, then that plasma metallurgy, carting, welding, plasma CBD, atmospheric pressure plasma spray coating, then nanosynthesis. There are so many applications of plasma nowadays, and you know that plasma is usually categorized into two types. One is thermal plasma and one is non-thermal plasma, as far as industrial plasma is concerned, apart from this fusion plasma. So, in industrial plasma mostly either it is a thermal plasma or it is a non-thermal plasma. Both of them has huge applications, and they are now increasing day by day. So, these are universe, what he told that more than 99% of our universe is in the form of plasma. Galaxy, nebula, our sun, all of these are in plasma state. And really the kind of state where we are on the earth, it is it is a very much exception kind of object if you consider the whole universe. Now, how to get the plasma? We told that you take any solid, then you just keep on pumping energy into it, then it will become gas, or directly it will be it will be reaching the gaseous state. Then if you put more energy, then liquid will become gas, and if you keep on pumping energy, then this gaseous substance will keep on heating, and a time will come when the electrons will have sufficient energy to come out from the respective atoms. Then atoms will be ionized, and the state that has just arrived after ionization, when there are sufficiently large number of ionized particles and electrons together existing, the state they reach is the plasma. So, this is the simple thing how to reach plasma. Just keep on pumping energy, and ultimately you will reach the plasma state. So, about charge neutrality, plasma is formed of electrically neutral substance. For example, as I told you that if you keep on heating, then a time will come when the substance will reach the plasma states. Now, suppose we have taken a piece of iron, and as you know, this is neutral. So, the number of protons and number of electrons in each atom, they are just exactly balanced. Now, when you are pumping energy into that, then this solid iron will become liquid iron, and then it will vaporize, and then a time will come when they will be ionized. But initially there are equal number of positive and negatively charged spaces. So, finally also the same will be there. Initially if it was neutral, finally also it will be neutral. So, we can understand that mm, uh, there will be collection of equal amount of positive and negative charges. So if there are doubly charged ions, then there will be two electrons coming out from that, so they will balance each other. Similarly, if there is a singly ionized, one electron will be coming up and the ion will be singly positively charged. So they balance each other, and the net charge always remains 0. Now, whereupon the plasma gets its potential to react in a very different way compared to the ordinary gas. So, this is basically the long range Coulomb force that contributes towards this. The peculiar behavior in plasma originates from the simple fact that charged particles interact with each other via long range Coulomb force. Now, you just think about this, that with distance the electric field decreases as inverse square law of distance, but the number of charged particles increases as cube of distance for uniform density. So, this gives rise to possibility of coherent addition of electric and magnetic fields of an assembly of charged particles. Collective mode of behavior in plasma arises out of that. Now, molecules in ordinary gas interact through short range forces. So, such collective behavior is not possible there. So, the physics of plasma, when you are studying here, the collective effect is very much important. So, it is essentially a many body problem. Now, plasma is usually characterized in terms of temperature and density. So, depending on that, most of the plasma that is there in the universe and in man-made systems, they can be categorized like this, as shown in this graph. So, here you can see that this is solar corona, and this is ionosphere, this is a gas discharge, these are arcs, and these are laser fusion and fusion reactors. These are tokamaks. So, you can see that the temperature in electron volt, it is starting from here, say 0.1 electron volt to 0.01 electron volt, and is raising, and it is reaching here 10 to the 5 electron volt. Now, laboratory plasmas, usually these gas discharges and this arcs, image regenerators, so they are mostly in the labs they are being formed, and you will be coming in this course coming across many systems which are dealing with this, either glow discharge or arc discharge, or cold atmospheric pressure plasma discharge. And this course mostly avoid this region where you are having this fusion kind of plasma, whether it is a laser fusion or it is magnetic fusion. So, devices, they are called tokamak. So, this region we are not considering. We are basically confining us within the industrial plasma, which are mostly in this zone. Okay. But one thing you should know, that when you are dealing with arcs, you see that the number density is of the order of 10 to the 23, 10 to the 24 per meter cube. Now, when this is your arc system, so that density is quite high. This is mainly because the arcs are generated at atmospheric pressure. But when you are going for glow discharge plasma, usually they are at low pressure, so you naturally get the density less. It is of the order of 10 to the 17, 10 to the 18, they are very common. Now, nowadays, one is atmospheric pressure cold plasma discharge. There, because of very less ionization, again you get a number density of the 10 to the 17, 10 to the 18 per meter cube kind of thing. But there, it is a very highly non-equilibrium plasma, where you are getting the electron temperature is quite high, maybe 3 to 4 eV it can reach up to, but the gas temperature is quite low. It may be just you can touch it by hand, so it may be just 300 Kelvin, around that it will be like that. Okay. So, they are very interesting. We will be coming across that as we move with the course. Now, you have now understood that the key thing to reach the plasma state is to ionize the substance that you are having. Now, in the periodic table, we do have elements, and as you go on increasing with this Z, then you see that the ionization potential shows a very zigzag path, and that is having a decreasing trend. You see the peaks, these peaks are for the the inert gases. So helium, neon, argon, krypton, xenon, radon, so they will be showing the peaks because they are having inert gas configuration. Now, as you are increasing the Z, this total number of electrons are increasing, so the orbits, they are becoming larger and larger, so they are now the outermost electron are less influenced by the nucleus, because the diameter of the orbit is becoming larger, so influence is less. So you can easily ionize the electron from the outer orbit. That is why the falling trend of the ionization potential that is coming, but because of this field orbital and half field orbital, this zigzag distribution, what you are seeing, that is arising because of that. But this is very much important, because you need to know how much energy you need to put to remove the electron from the outermost cell. This is the ionization potential. So you are seeing here that this one is 13.56. All of us know. So this for hydrogen, and next one is so high. You see that it is around 25 electron volt, 24 point something it will be. Now almost double this value. So this helium, it will be very difficult to ionize. So like that, when you are going for lithium, because one electron is just more than the helium configuration, so you can just easily strip that out. So that is showing a very low ionization potential. So similar way, you are getting a zigzag path, but this graph is very much important for us, because whenever you want to create any plasma, the first thing we would like to know what is the ionization potential of that particular atom. Now, when a system is in sort of equilibrium, then the composition of the plasma can be obtained from Saha ionization equation. So Professor Meghnad Saha actually gave this equation in a bit different form, but nowadays this equation is always presented in this form. And here where you are seeing that nr plus 1 Ne by Nr. So this is a kind of generic equation. For example, suppose R equal to 0, then that is neutral. Now R equal to 0, so this is becoming N1. N1 is the first ionized state, and this is N is the electron. So what you are getting a relation that Ni Ne by N0, that is neutral, then ion density, and then electron density. So that ratio is going like this. So Z are the partition functions, T is the temperature, E is the ion is the ionization energy, and if you solve this equation, then you will be able to get the what is the composition of the plasma. So we explained in our class that for a 5 species system for argon, for example, so we do have this argon neutral, then argon first ion, then argon second ion, argon third ion, and electron. So how do we write that equation? That we explained very well over there. And for the first ion, we are writing that N1 Ne by N0. For second ion, N2 Ne by N1. And for the third ion, we are writing as N3 Ne by N2. And on the right side, you are seeing that these are the partition functions. So this is the first ion's partition function divided by the neutrals. Similarly, second ion by first ion, then third ion by second ion. Now this U1 is the first ionization energy, it is the second ionization energy, and it is the third ionization energy. Now the thing is that when you are dealing with this kind of equation, what you are seeing that Saha ionization equation just gives you these 3 basic equations. But what you need to know, there are 5 unknowns. For example, argon, argon plus, argon double plus, argon triple plus, and electron. So they are together 5. But you have only 3 equations. So it is not, you cannot solve these 3 equations for 5 unknowns. So another 2 unknowns, 2 equations basically we require to solve this set of equations to get information about all the species that is there in the plasma. So how do you get that? The other two equations here we got from the fact that these electrons are coming out from the ions. So each single ion is contributing 1 electron, double ion is contributing 2 electrons, and these triple ions are contributing 3 electrons. So altogether they are contributing the total, electron number density. So these equations is the fourth equation, and the third one is the pressure, because we have generated the plasma at certain pressure, and that pressure and you know that pressure is, if you follow the ideal gas equation, then P is equal to NKT. So N is Ne plus N1 plus N2 plus N3. These are all the species that is there in the plasma. Okay. Sorry, in this actually there will be one, N0 also will be there. In this equation there is one N0 is missing. So this will be Ne plus N0 plus N1 plus N2 plus N3, because these neutrals, if they are there, they also will be contributing to the total pressure. So you need to correct this equation as P equal to Ne plus N0 plus N1 plus N2 plus N3 into KT. So now you have 5 equations and 5 unknowns, so you can solve these equations. So in this review, what we have reached so far, that we are now in a state so that we can tell what will be the composition of the plasma depending on the type of atoms that we have used and the temperature that is there. So the ionization will depend on the temperature, the ionization potential, the partition functions, all these things together. Okay. Now for this particular problem, this argon, argon plus, argon double plus and argon triple plus systems together with electron, we have 5 species, and how they are varying with temperature up to 40,000, or here rather it is I think 45,000 degree Kelvin, it has been plotted, and you can see that how it is varying. Initially when the temperature is very low, none of the argon atoms are ionized, so you are getting fully argon. Now you know that mole fraction I have plotted over here. The mole fraction is the number density of the particular species divided by total number density. Now initially the density of the gas is only argon atom, and total density is also that, so that ratio is 1. And as you keep on increasing temperature, see at around 10,000 degree Kelvin, what you are seeing that the argon starts getting ionized, and that is the first ionized state. And you are seeing that electrons are exactly following the argon plus curve, because each electron is coming from each ionized argon atom. So that is why they are following the same graph. But when it reaches around 20,000 degree Kelvin, you see that double ionization starts. That time each double ion is contributing 2 electrons. So that's how the electron density is now increasing, and that is now not following the argon plus line, because argon double plus started contributing electron, and that is twice the contribution from argon plus atoms. So that is why now you are seeing that the electron density curve, electron mole fraction is now getting separated from the argon plus curve. Okay, now when you are reaching around 30,000 degree Kelvin, then third ionization starts, and you see that this electron mole fraction gets another jump, because now each argon triple plus atom is contributing 3 electrons. So that is why you are getting another jump over here. So now you can very well understand how this graph is originating for the mole fraction, how the ionization scenario is progressing with temperature, and there is another parameter which is shown by the dotted line. This is basically the non equilibrium parameter theta. This is the ratio of T by Th. So with that, how the mole fraction can vary, that has been shown here, because this is a monoatomic gas, this argon. So the effect is quite low, but if you are getting a diatomic gas, you will see that this non-equilibrium affects the composition very, very significantly, and when the composition is affected, everything like the thermodynamic properties and the transport properties, all of them are getting affected. So the degree of non-equilibrium, that is ratio of electron to heavy species temperature, that affects a lot the composition of the plasma when you are considering the molecular gas compared to the monoatomic gas. Now, once you know the composition from the ionization equation, you know the number densities, so you can find the density. So these are all thermodynamic parameters. Specific energy you can calculate like this, and you know that specific energy of a particular species you can calculate like this, and specific enthalpy, that is nothing but joule per kg, you can calculate from the specific energy adding this kT, and specific heat you can calculate like this, taking the derivative with respect to temperature. So, all the thermodynamic properties you are getting out of this. Next, it comes that when you are going for this molecular gases, and for that actually those this ionization equations, they are not exactly like the one that you have seen in the case of argon. They become a bit complicated, but through Gibbs free energy minimization you can derive all of them, and some of them look like that, and that we have explained in our regular classes. So, you need to remember that the psi equations can be derived from the Gibbs free energy minimization, and their form looks like this. So, basically they are left hand side, they are all the ratio of number densities, and on the right side this is the rate. So, this rate is written like this, they are in terms of these partition functions, and this reaction energy, like reaction means it may be first ionization, dissociation, second ionization, like that. So, those energies are listed over here. These energies you can get from literature, and these equations can be solved in the same way as you have done for the argon. So, for a this N2O2 plasma 80-20 composition, you get the distribution of various spaces, like this is for N, this is for N plus, this is for O plus, this is N double plus, O double plus, and this one pink one is for electron. So, you can see that how they are varying, and as you are increasing the non-equilibrium parameter, you see that how the graphs are shifting. So, that is what I told you, that these non-equilibrium factor, your degree of non-equilibrium is very much prominent in the composition when you are going for this diatomic or gases which are composed of multiple atoms. Like for example, you can go for CO2, or you can go for NO, or you can go for N2O2. The effect will be very much prominent, this non-equilibrium effect, that is T by TH. So, you can see here 1, 3, and this is 2, and this is 4, and you can see they are distinctly different from each other. So, I stop here for this class, and after a little break I will be back again, and I will continue with the same thing.